Okay. Let us start the Globia seminar series number 5. So we are currently in this topic following infrastructure for deploying image analysis workflows. And when we say workflows, I think we better be a bit specific about what it means. So that I'm showing one of the schematic figure about what we mean about workflow. So there are 3 different concepts in this figure. So one is collection here. Other is workflow. And then there are component. Many components in this collection. So what it means is that component is something like an implementation of some specific image processing or analysis algorithms. For example, like if there's a plugin for Gaussian blur filtering, that's one component. And then if there's a plugin for, let's say, connected component analysis, that's one component. And collection is like an image or scikit image that includes, that collects all those components and pack them as a single packager. And mostly what we get as download file is a collection with many components inside. What we do when we do image analysis is that we create workflow, which we choose certain components one by one to create a workflow that we can, starting from the raw biological image data that you get from microscope, and then you do some processing, analysis, processing, and then after steps of those processing using components, we come to some numbers, measurements, plots, stats, or visualization. So this is the procedure where when you make workflow, you have to choose the right component and then put them into the right step in this workflow. So this is a workflow. And what contrasts collection and workflow is that collection is like, it's made and maintained by software developers. And then while the workflows are created by analysts, BioImage analysts. And the difference is that there are different kind of values or goal of how you make it. So in case of this collection of components, what matters is speed. So that we want to have faster algorithms, and there's a kind of understanding that faster is better. And another thing is generic. Generic means that the component applies to wide range of input data, so that more general, it's considered to be better. So it's like mathematics. So general function is better than specific function. So on the other hand, in case of workflow, what matters is more about accuracy, so that how scientifically adequate. And then so that's kind of a bit different, because sometimes we say that even the speed is slower. We like it more accurate and scientific rather than just fast. And the biggest difference is that workflows are in many cases very specific, so that these are the workflow in many cases cannot be applied to many different situations. It's very specific, specifically designed for certain biological questions. So that that's kind of different from what the general software are with these collections and components. So here now, so that we're trying to deploy image analysis workflows. So if you think about this kind of difference, deploying workflow means that you want to show how scientifically adequate the workflow is. And it's also that how nicely it works to measure something scientifically. So that's a kind of difference from this benchmarking or collection of components. So that was kind of a short, rather long, explanation about what workflow we mean. And then here now, so we have 4 speakers. So initially we were inviting only Christian Tischer, but now we have 4 different people talking about NextFlow for BioImage analysis. And then the first one is Christian Tischer. His nickname is Tischi. He's the head of Center for BioImage Analysis, EMBL Heidelberg, Germany. Tong, he's a senior software developer from Wellcome Sanger Institute in UK. Tim Buchholz, he's a bioimage analyst at FMI Basel in Switzerland. Miguel Ibarra, he's a PhD candidate in University of Heidelberg in Germany. Okay, so let's welcome those speakers, and then I'll be listening to all these people. But before that, Krista will give, so she's a community manager of Glovius, and we'll make a short explanation about the current status and some information to update you. Thank you.
So I hope you now can see my screen. So what I wanted to point out is that GlowBias now has a YouTube channel, and so far we had only uploaded the seminar series videos on there. But now we have additional information on there. So one is actually a video done by the communication group, which is an interview with Kota, Elnas, and Robert about the idea behind GlowBias. And then we have started also to upload sessions we recorded at the first workshop, which we did beginning of November last year. That was the first in-person workshop, and the sessions that have been recorded will be uploaded bit by bit, and we will create some playlists. So if you are interested in this and watching it, you are welcome to actually do this. And that's all for me already. So now I hope I can go back. And now, so now I hand over to Christian.
Yes, thank you, Kota. Thank you, Krista. So now I will try to share my screen. There we go. So you can see the slides. Good. Okay, yeah, so welcome to a session on building bioimage analysis workflow with NextFlow. So I will kick it off by an introduction to NextFlow. Then Tim Oliver will show how he uses NextFlow in the microscopy facility in Basel. Then we have Miguel talking to you about some actually reusable workflow, right? So Kota said some workflows might be specific, but you might also be more ambitious and might to have it reusable. And about NF Core, which is some special version of NextFlow that is actually made for reusable workflows. And then Tong will share with us some ideas how we can use NextFlow for analyzing really big images. Okay, so why NextFlow? So, I mean, there are actually many workflow management systems around. And as you might know, also people are start building now some specifically for bioimage analysis. But myself, and as you see, I'm not alone. There's 3 other speakers. We thought, why not use something that already exists and has proven to be useful. So, and that's one point about NextFlow. It has been around, I think, for about 10 years. And as you can see here with the GitHub stats, this is pretty active, right? So it's not just one person that cares about this, but many. The other thing is there's also now a company called Sekera that actually just built on top of NextFlow. And the good thing about this is that they then also just can earn money to further support this project. So it should be relatively stable and well maintained. At least that's what I hope. So now other good thing about NextFlow is it's actually really easy to install. So you just need to type these lines of code on your computer and then you have it. So that's an advantage, for example, compared to other things like Galaxy that I think you just cannot almost install, but you have to go all in on the web. Caveat, I think you may be able to install it on all operating systems, but running it requires some sort of Linuxy operating system because it actually builds on the Linux philosophy. So it will not just run on Windows unless you have a Linux subsystem there. So that's definitely something to notice. And in a nutshell, this slide actually shows you what NextFlow is. So actually what you need to do to use NextFlow is write such a script. Yeah. So it's just one text file that you have to produce. And there's, of course, a lot of documentation on the internet. ChatGPT from version 4.0 on is actually quite good at writing these things for you also, if you want to try. The basic concept here is like what Kota said. It matches very nicely to what he said. So the workflow is composed of components. So the components here would be segment and measure. And here you define the workflow. So the idea is you segment images, and the images, they are actually up here defined. This is basically files that live on your hard disk. Just say all the TIFF files in the input directory. Then they will be all segmented, and the output will be label mask images. And then you measure. And actually here in this case, we want to measure not only the morphometry, but also the intensity. And then you can do NextFlow things like say images.join labels. Then it will always put together the correct image with the correct label, and then you can analyze them together. So this is the kind of text that you have to write. And then, for example, the segment process, it has so all of them have an input and an output. So which in these cases are just two paths. And then you run something. And here, for example, we first run cellpose, the command line tool, and then use the save TIFF function to create a TIFF output. And then for the measure here in this toy example, I am pretending I use Fiji to run a Groovy script, which would take the image and the labels and then create a table as an output. So one point here is this is, I think, really doable. I think this is actually as minimal as it can get in my eyes. I don't know how to do that even easier. So I think they did a good job. The other message is this is not specific to any programming language. So here we run Fiji and then cellpose, and you can run Python and NextR and whatever. So it's not bound to any programming language. The only thing you need is something that is command line executable in a Linux style, right? So that's basically what you need. Okay, then to run this script that we just wrote, right, which is called script.nextflow, for example, we just type this. We specify where's the input, where's the output, and press enter, and then it does it. And the other really cool feature of NextFlow is it supports many platforms on which it can run. So if as executable you put nothing, it just runs on your laptop. But for example, if you happen to be on a Slurm cluster, really the only thing you need to do is write here executor Slurm, and it will do all the job submission for you. And here you can also specify how much it should parallelize. So basically, if you have 100 input images or maybe 10,000, then it would parallelize here across 100 jobs. Or you can also leave that empty. Then I don't know, maybe it just parallelizes. I don't know on what's the default. But basically, the whole point is this pipeline will run in parallel for all the images that you have up here. So this is also quite nice. And then they support many execution platforms. So not only Slurm cluster, but also, I don't know, whatever, Google Cloud, some AWS things. So this is also quite good. So you don't have to rewrite your code every time you change your hardware. Okay, then another important thing is that for each process, you can actually manage how many resources you want. And then also what's quite nice is a strategy, what should happen if it crashes because it's out of memory. So for example, here you can say, hey, if you crashed because out of memory, please just try again. But each time you do it, just increase the memory, right? So this is actually really a lifesaver if you're working on a computer cluster. And this is all done provided here for you already, so you don't have to write this code yourself. Then, of course, the other big question is, where does all this software come from? Right, the cell pose has to come from somewhere. I mean, either it is just on your computer, and then it will just find it, right? Because your computer just knows where the cell pose thing is. But you could also say, hey, no, I don't have it, but there is this container in the internet. Please download it for me and run it with this container. And again, this is already supported. Instead of container, you could also here write conda, and then either you have the environment on your computer or you write a whole installation recipe, and also this is imported. And here on the right, you can see they have many other things they support where the software actually comes from. Then if everything ran, another good feature is you can actually get the report. It kind of shows you what your pipeline is, how it looks like, how these jobs ran, how many CPU they needed, how much memory, and so on. So that's, again, if you have big data, quite nice that you can just look at this, and again, it's just a one-liner. And okay, I think this is basically my last slide. That's why I cannot continue. Okay, so I gave you now just a kind of overview, and I will hand over to Tim Oliver, who will show you, I guess, one implementation of how to use all of this. So
before this, can I just
yes,
administrative thing, but if any of the audience has looking at this seminar have question, please write it in the chat section so that later we can just go back to question and answer session for these things. Thank you. So please hold.
Yes, I will now share my screen here. Can you see my team? I mean,
yes,
the team I'm part of.
yes.
So yes, my name is Tim Oliver Buchholz. Hello, everyone. I work in the Facility for Advanced Imaging Microscopy. This is the team. So we have here our head, Laurent Gellmann. Then we have Flore, Sabine, and Alex, and Mathieu. They know tons of microscopy, EM, light microscopy, spatial transcriptomics. We have Short and Giuseppe, our IT liaisons, and then there's Jan Ecklinger and myself, and we are the two BioImage analysts in the team. I quickly have to move this Zoom bar around. All right, good. Yeah, and the job of myself and Jan is to provide image analysis workflows to the whole institute, to all the users that walk into our offices. And the way we are doing this now for more than 1.5 years is by implementing for each project request our project template, which is just our organized, standardized way of how to document, which infrastructure we use, how we organize the data, how we play around with new algorithms, and most importantly, to have reproducible source code and keep track of config files and what do we run, which dataset did we run at what point in time. And just very short, since we use project templates, I think we got much more efficient in development of high quality image processing and analysis pipelines. I don't want to get into all the specifics of our template, but I want to specifically tell you how we use NextFlow to make our lives even easier, and how we make sure that our users can submit an NextFlow workflow without too much fear. Let's put it like that. All right, so you saw the source and runs directories here, these two gray shaded things. So in the source, this is our source code. So it's versioned source code on GitHub. And if we want to obtain some derived data like segmentation masks or processing results, we want to only produce those with code that is under version control, and with code that consumes some sort of a config file, which allows us to run the same piece of code with different parameters on different datasets. And these different config files, we keep track of them inside our runs directory. So for each raw dataset, we have a subdirectory there that contains the different config files. Bit abstract like this, so let me open it in my IDE. So we have here the source directory, and we have two processing steps, segment and measure. There's also visualization, but this is not part of NextFlow because human interaction is important. So yeah, each of our processing steps we do mostly at the time in Python. So that's why it's all Python files. But as Tischer showed you beforehand, it can also be a Fiji script, a Groovy script, whatnot. The core part for each processing step in our case is that we have a config file or a config, which is a pedantic model, super convenient with the type annotations and validation and whatnot. And these configs, these pedantic models, they are consumed by our run scripts. And of course, if this is the first step, they usually write out the next config file for the second step and so on. And one very important decision that we took here is to really keep these individual processing steps as command line executable scripts. So you can go and process all your data by calling S01 segment run and then S02 measure and do it all manually. And if you have a huge data set, that might not be feasible on your laptop, but it's possible. And the reasoning behind this is in case our users leave our institute, because I don't know, got a new position somewhere else, they should still be able to execute their pipelines on their laptop. Maybe they have to finish up some paper or something, or need to rerun a portion of the data set. So they can do it. However, it might not be convenient, and that's why we use internally NextFlow to orchestrate this whole processing. Another aspect is maybe one day we figure out that NextFlow is not the tool we want to use anymore, and we don't want to disentangle our processing functionality from the orchestration functionality. This is also something which is nicely supported with NextFlow, because as you have seen before, essentially you have a workflow file where you define your processing steps. They have input parameters, output parameters, and then everything is just a command line executable. So in our case, it's Python managed with Pixie, about that a little bit in 2 minutes. And you just provide your config files. So one thing that is a bit different in our case to what you've seen before is that we handle everything via config files. So this config file can either just contain the path to a directory, which contains a bunch of TIFF files, and then it's the job of this run.py to parse all of that, or the config file can already contain a list of files that it should process. And then whatever this script writes out must be a measure_config.yaml, which can again contain a list of files and parameters or whatnot, which is then consumed by the next process. And they are organized like this inside this workflow. Now you see here that I have annotated both processes with labels. So we have a CPU label, only CPU in this case. And what they mean is defined in the NextFlow config file, where we can define profiles. So we have a standard profile, which is the one used by default. So this is the local executor, which I have limited here to 4 CPUs of my 12 laptop CPUs. And then I define for all the processes the different labels. So here I only have CPU, but you could have large CPU or 100 CPU. And you can define for each label how many resources it can have. This gets a bit more interesting if you go to a Slurm executor. I say here, yeah, I want to have the Slurm executor. I can also define a rate limit, so only submit 50 jobs per 60 minutes. And do not put more than 50 jobs in the queue at any point in time. And then here the CPU label gets a bit more interesting because I also say how much memory I want, to which queue I want to submit it, and can even provide more cluster options. For example, if I have a GPU resource that I need, I would also define it here. Now, the tiny example that I show here is actually in here in this example project. There's only 2 steps. It's only segment the measure on tiny data sets, but we use NextFlow also for these kind of things, because just calling these 2 steps manually, it's fine once or twice, but if you have to do it multiple times, it gets really annoying. But of course, what do we do if we have like a big multi-well plate? Just doing this sequentially is not really making use of NextFlow, and there we usually add a parsing step on top, which parses all the files and then sees we have 100 wells, and then this parsing script makes a decision how to parallelize, either over all rows or all columns or over all wells, and then writes out config files for each of those. And then NextFlow collects all these config files and starts the segmentation and measuring steps automatically. So yeah, this is NextFlow. It can be maybe a bit daunting if you are not used to writing scripts and do programming and all this kind of things that we do in our daily work. And of course, not everyone would be too happy to learn that you need to type NextFlow run and then command that and parameter X, Y, Z, and I don't know what. And the way we try to tackle this is by employing very useful tools. One is the Pixie. And Pixie is an environment management tool for Windows, Mac, and Linux. And it's all built around this pixie.toml file where we can define on which platforms it should run. And more importantly, there is a very cool thing called feature where we can define specific packages that we want to install for only a subset of platforms. And next to that, we can define tasks. And tasks are just aliases. So the task is called NextFlow, and the command this thing executes is quite a bit. So it first does some commit logging, then it changes the directory, and then here is the long NextFlow command calling this workflow with the respective config files. Now, for the user, no, wait. Now this might still be a bit complicated because, well, you need to know what to type, Pixie run, what not. So we even make this more simple by using mkdocs documentation. So this is markdown files which get rendered into this beautifully looking static websites. And the cool thing that we can do here is we can type all the commands and put a little copy button. And so the user only needs to know how to copy paste stuff from a website to their command line. And if we have some variables, like here, dataset and slurm account and mail to that change all the time and are specific and necessary to type out for this workflow, we make use of this mkdocs user-defined values plugin. And now the users type up there the dataset name, the slurm account, and the mail, and the commands get all automatically filled out. And now they really only need to know how to log into our slurm cluster, how to change a directory, and how to copy paste commands. And that's all they need to do. So, to summarize, from the top to the bottom, mkdocs for the documentation to make it easy accessible, Pixie for the management of all our dependencies and versions and different commands that we need to call, and NextFlow does the heavy lifting in orchestrating and parallelizing our processing. And with that, I'm at the end of my bit. I hope I didn't steal too much time.
Thanks, Tim Oliver. Very sophisticated. I'm impressed. Then I think, Miguel, your turn.
All right. Thank you, Tim, and thank you, Tischer, for introducing NextFlow and in general, all the capabilities that we have with it. Now I'm going to go a little bit more into the bioimage analysis
We see
side
the
and how.
presenter's view.
Oh, you only see the presenter's view? Oh, no. Wait, let me flip this. Perfect. Yes, as I was saying, I'm going to go more into the reusable component of NextFlow and how, at least in Shapiro Labor, use it for bioimage analysis. First of all, I want to thank all the members of my lab that are constantly pushing for NF Core and NextFlow for pipelines. And then we have already mentioned NextFlow as the tool, the bread and butter to do workflows. But now, how do we want to achieve this reusability part? To do this, we rely on a community-based approach on NextFlow that is called NF Corp. It's a pipeline development, but based on community. A way that you can see this is, let's just call it the bioconductor for NextFlow pipelines. It already provides like a lot of templates, code guidelines, a very strong community that is always willing to help, and even resources for an easier development of pipelines. The pipelines and modules here implemented are subject to like very rigorous testing and multiple review process. So you can ensure that all the components that you use for the pipelines or that you develop for the pipelines are going to be able to be reusable for different circumstances. The pipelines that we mostly use are multiple choice microscopy. Some of you may know it as MC Micro. It's still under development, and together with Molcar, which is a pipeline that is not only for molecular cartography, but any other fish-based method, are the core for our projects. MC Micro started originally as a NextFlow only initiative. We tried to make a scalable modular image processing pipeline. This was started by Dennis Shapiro, but we realized that at some point that it lacked the flexibility that we needed to cover for more projects. And thus, like we started to develop more for NF Core. MC Micro itself is a pipeline that tries to cover the typical image proteomics pipeline. This is just an example in which basically you can go through different steps of the process, coming from your raw data in which you have your tiles, going to stitching, bringing your tiles together, illumination correction, and then once we apply this for each channel, we do some registration, segmentation, and quantification all together. These steps can be done with many different tools. You can use, for example, Stardist for segmentation or CellPose. You can try to do a registration with Ashlar or Palom. There are multiple tools for each step of the process, and different projects will require different tools or different combinations of them. At that point, we realized that we needed a more flexible solution. If well, it's okay to still have a more or less standardized pipeline that will allow you to process everything from end to end. You will still want to have something that is flexible enough that is able to adapt for different circumstances. That's where the idea of NF Core MC Micro came from. In this case, all the modules that we had already prepared in a pipeline for a NextFlow only, we migrated them to this NF Core community, and we're trying to follow every standard for it to make it available for a larger public. I'm gonna show you now some of the instances where we use this pipeline. One of them here from the group is for a myocardial infarction in murine specimens, in which we have the Luna4 Comet machine, and we basically do analysis based on this beta version of NF Core MC Micro. In this, we added a very particular model that is very useful, which is autofluorescence correction followed by a background subtraction. This backsub module that we added now is like implemented already into NF Core, but it can be also used for any other pipeline down the line. We also have use cases for collaborations. In this case, we use analysis for brain metastasis, in which we also needed to modify a little bit more. And we needed not only to quantify the markers, but also identify spots of a very particular protein. So we can also quantify it, but in a different manner. In this case, we added a spot detection module for this, and you can see here on a modified pipeline, the metro map of the pipeline that we use for this instance. We have also developed pipelines that unlock different parts of the biology. In this case, this is a tool that I developed as part of my PhD project that is called micronuclei, in which I use different segmentation methods and eventually just like output, and I'm able to quantify the number of micronuclei and thus getting an approximation of chromosomal instability using an NF Core approach and the modules that we have already created. We are also trying to implement this in a more translational setting in Heidelberg, the Translational Spatial Profiling Center. We are also trying to implement this for all of our analysis. And then Molcar, an effort led by Krešimir Bestak, is a pipeline that analyzes end-to-end a single molecule fish data. Originally was developed for molecular cartography for result, but it's being extended to accommodate to all the single molecule fish data platforms out there in the market. There are many use cases for these tools. We know that the pipeline itself is a very particular endeavor depending on the project, but we believe strongly that having standardized modules and standardized pipelines allows down the line for the users for the users and developers to make a more seamless development and understanding of what is going on. If you want to get a little bit more information, you can always scan the QR code, and I will pass this to Tong. Thank you.
Hi, everyone. Nice to meet you. Let me share my screen. I'm Tong Li, by the way, from Sanger. Welcome, Sanger Institute. So what I will be talking about is out-of-memory processing with NextFlow. So the reason we are interested in this part is because at Sanger, even though we're known as doing a lot of sequencing in the institute, but now we are more interested in imaging as well because of the spatial transcriptomic projects and the technology. And with that, sorry.
Do you want to press the play button so that it's full screen, or?
Yeah, sorry. Good point.
Okay.
So yeah, for those who doesn't know, image-based spatial transcriptomics is a way that you profile your gene expression on your tissue without losing all the spatial information. So very briefly, the way it works is like you section your sample, you put it onto a cover slip, and you do staining, and you do multi-run stainings. And for every single run, you do a capture of the images, and then you analyze all the images from different cycles. Of course, you need to keep the tissue intact because the spatial information is crucial for spatial transcriptomics, and you don't want to lose it. That's the reason why we really need to process large image data, and we cannot just tell the way that randomly and then process them together. So for that reason, we need to deal with large image data set. And we have implemented, without going into all the things in details, we do have a in situ sequencing image analysis pipeline for reference. In situ sequencing is one of the spatial transcriptomic technologies that people are using in the world. And for that, we implemented NextFlow-based stitching, registration, segmentation, and the decoding of the transcripts. And some of them, sorry, I just need to make this shorter. And this is better. Yeah. And because I was invited to talk about out-of-memory image analysis, so I will skip the stitching and registration, but focus on the segmentation, which has been already covered. So in our pipeline, we haven't innovated a lot of the new things. The major kind of contribution that we are doing is like, because we're dealing with large images and the canonical cell pose doesn't really handle the large images very well, you often got out of memory issues, especially if you are dealing with GPU-based segmentations. So we need to think a way of workaround of that. The way that we are doing, like very simple, we tile the image into different regions. It can be just a grid, as you can see on the left. And then we run segmentation, just normal segmentation on each one of them, and then we merge them together. So it sounds easy, but if you precise the default output of cell pose, which is a label image, you will have trouble. You will have issues just merging the cells that are at the intersection. For example, at the schema that I'm showing on the in the middle left. So especially it's like you will be dealing with ID issues. For example, the cell in the middle, should you assign an ID to the left or to the right? And knowing that you also need to reindex for each single tile. So that information, how it passes through different steps is quite a problem. So for us, our strategy is to run segmentation, but instead of keeping the label images, we keep the polygons. So we don't have ID issues. We only assign ID at the very end when it's merged together. And explicitly, what we do, the first step is to, for sure, generate tiles. And for that, you can use actually any softwares or tools or scripts you want. What all I need is just the bounding boxes for each single run, for each single tile that you want to process, and with the name, which is also optional actually. The crucial part is just the bounding box. You can have many ways. You don't have to follow the example that I'm giving, but as you can see, it's pretty short. Then you run the segmentation, which I've already skipped. Actually, it's just runs canonical cell pose on that tile. The only thing that I want to, maybe I need to highlight is like, the segmentation needs to run, sorry, it is this part. When you run the segmentation, you need to explicitly tell which is the bounding boxes. And if you want to use that command line interface, as Tischer was showing, you need to find a way to pass it, either through the way that Tim Oliver was using configuration file, or you pass explicitly with the command line interface, like I'm highlighting here. So this is up to the software developer, whether they want to use a configuration file for everything or explicitly state every single parameters with the command line interface. So then you run this, and then you merge all the polygons together. And the way that we are merging, again, this is the whole script is like the one on the left, so really short. The idea is like you shrink a little bit, you shrink by 1 pixel before you merge, you shrink a bit to separate all the segmentations or separate all the polygons. Then you simplify, because otherwise there will be too much vertices and that will be memory hungry. That is just for efficiency. And then you simply merge them together using the unary union, and which is provided function in Shapely. And then you buffer 1 pixel to give the original size of all the segmentations. So with that, you will have all the cells merged together from all tiles without losing any spatial information. So as you can imagine, this tile segmentation can be applied with different algorithms, as long as the actual segmentation steps give you a polygon instead of the label image. So this is what we've implemented at Sanger. We can choose between cell pose and star dist, and the only differences is like you change the method that you want to use. So of course, for cell pose, we need to post-process a little bit to convert a label image to polygon, but that's what we need to do to make sure that is compatible with this tiled workflow. And as you can imagine, the list of supported segmentation can expand. You can support Mesmer in the future, and if for spatial transcriptomics, we can also use Sager, but that is we will need a little bit more information in addition to images. We will need transcript location for that as well. But anyway, the idea is the same. This can be really scalable and can be extended to different technologies. So we've applied not just to segmentation, because if you think about this, the merging polygons is a way of merging the output data from the step in the middle. But we can also merge different things. For example, which is a peak calling. For the peak calling, you still do the bounding boxes funding, and then you do peak calling in the middle, and then you merge all the peak locations in the very end. But with that, you don't need to do all the buffering, and you don't need to do that shrinking, etc. You just merge all the peaks. Here it's to ensure we don't have a duplicate peaks. We buffer a little bit by the size of the diameter, and then we make sure all the touching points are merging together, and then we take the centroid of those peaks. So as you can see, with different tasks, you may need different merging scripts. And with that, we are thinking, what are the elemental things that we can actually create a sub workflow instead of just one tools? Because we are interested in all the large image processings, and there are many more things that can be scalable, but which are not yet. For example, the registration that I haven't talked yet. There are a lot of great registration tools, but a lot of them struggle with the memory, and some of them really need optimization. And can we use this tiled way of running segment registration as well? And last but not least, we're also wondering, because we are developing these pipelines, but we are having trouble to convince people to use NextFlow. So that's the question we're asking, like who needs to learn workflow managers and who needs to run workflow managers? These are potentially two questions, because developing is one thing, but running should be easy, as what has been shown before. And that's all for my side.
Okay, so thank you all co-speakers, and then I guess, do we have questions?
Yeah, there are a few questions. So Ofra is asking whether QPath can be integrated with a NextFlow pipeline.
Ofra, can you specify? I think like in NextFlow, there should be something that has a defined input and a defined output. So the question is which specific input and output you would be thinking about, I guess. Maybe if you can add that to the question. But I think everything that is command line scriptable and has an input and an output can be integrated. So I'm not sure if QPath ticks that box. I think you can Groovy script it somehow, and then I guess maybe just put the Groovy script as one NextFlow step. So yeah, I guess probably the answer is yes somehow.
Okay, so next question is from Joel. How do you run NextFlow in your regular deployments? With Conda, Pixie, containers, or something else? What made you choose that option?
Maybe we can go make a tour de table. So I think we currently use the Honda, and that's just because that's what we started with, and it was somehow the easiest.
It's the easiest, yes.
Then Tim Oliver.
So we use Pixie essentially, and Pixie takes care of managing the environments. But the next thing I want to explore is actually Apptainer. So
Yeah.
containerization. I already found some tutorials to convert Pixie environments into containers. And then that would actually be my preferred way of running it, because it would also be easier to submit it to, I don't know, wherever you want.
Something that I forgot to mention is that NF Core modules by default should be implemented in Conda, Docker, and Apptainers. So you can already make sure that it runs everywhere, basically. At least for the NF Core part.
I think Tong has a strong opinion.
Not my personal opinion. I think most big institute has issue with Docker. I think a lot of HPC doesn't run Docker anymore. So different scenarios. When testing, we use all of them, Conda, Docker, Singularity, but in production, we only use Singularity.
Simon say also that it was great. Thank you all for this. And another question is from James. He say these examples are all very really cool. NF is a very powerful if it works, but new user people with limited command line experience will find it hard to debug. How do you support user with limited experience?
So maybe
I
I
will
start,
just-
and I think it's a bit similar to Tim Oliver. So we don't let users debug it. So we debug it, and then they just copy and paste one line of code, and that runs. I don't know what the others. I think it's probably for all of us the case, or?
Yes.
Yeah.
What I find very useful with NextFlow is that it writes tons of log files.
Mm.
So as long as they just tell you which run failed, there's plenty of information to debug it. I had cases without NextFlow where it's just like, it broke, but I can't reproduce how it broke, so that's much easier that way.
Yeah, just to add on top of what Tim earlier said, while using NextFlow, it's most like you are training a naive biologist to run your program like a programmer because of all the log file that is produced, so that it will help you debugging. So that's one point. The other thing is like I'm personally writing all the workflows with NextFlow. I'm not creating a test environment and then wrap everything into NextFlow. Actually, I'm debugging with it because all the supported features by default. So I'm writing everything from scratch with NextFlow. As long as I'm writing something that is more than 2 steps, I will start a NextFlow project. That's my personal behavior.
Good. So wait. So I forgot to introduce Paula Lanos. She's hosting this seminar from Broad Institute in Boston. And then another one who is helping is Laura Rodriguez. She's in Oslo. And then she's helping to make less traffic jam with the question and so on. Thank you.
Cool. The next question is from Joel. He say, for Miguel, what is the difference between NF Core NextFlow modules and the older Mac Micro NextFlow modules? Could you elaborate on the work needed and what changes when you adapted the old Mac Micro modules to the NF Core standards?
That is a very good question. Ideally, the user shouldn't see any change between the old MC Micro and the new MC Micro in NF Core. That's to begin with. If you want more of the specifics, it basically means that before, all the modules that went into MC Micro were a little bit disconnected. They were not really open to the community. Into the NF Core, we first make the modules available into NF Core, and then we use those modules to make a pipeline. So that means that all the modules that we put into NF Core are already reusable by default for anyone who wants to create a new pipeline or adapt it to any specific circumstance. That I will say are the major difference between the normal vanilla MC Micro and the NF Core one. And since we want to make the transition as unnoticeable as possible for the users, that's why it's taking us a little bit longer to get there.
Mm-hmm. Also, Arca, he asked about the documentation for this. So Miguel already answered. So if someone else want to check the link that Miguel post in the box of question and answers, so you can check there. Those are the question, I think. No, there is one more. Do you let NextFlow handle and cache the actual image data, or just metadata and each processing step loads the data from disk?
Guess not sure what the question is about. I mean, if you want to segment the image, you have to load also the data. So I don't know. That's one of my.
So I think each processing step is a standalone command line executable, so they don't share processing memory. So there's not like you can't move data between those. And otherwise, what we do, I mean, we only share paths to files between the processes. So we don't pass the big images. So if the segmentation creates a segmentation map, the segmentation process needs to write this map to a file, and then I pass the path to this file to the next step, and this guy loads it again. And my reasoning behind this decision was that processing the actual image data between processes would be fine as long as you run on the same machine. But if you're thinking about scaling up and processing on a cluster, it would mean tons of data transfer. I guess if I would do something in this direction, I would rather choose Task, which is more optimized on this level, I guess.
But yeah, maybe to clarify, maybe this is where the question comes from. I don't think we said it super explicitly, but like if you have one step, let's say Gaussian blur and then segment, like it must be in between a file on disk. So that's just the way how NextFlow works actually. So the whole image has to be saved on disk and loaded again. That's why I guess the modularity of these processes, granularity matters, right? Maybe you don't want to have, in fact, a Gaussian blur outside of your segmentation. Maybe just put it together so that you don't have to read and write too much. So I think this is a decision you have to make when you design these modules, which I think is not trivial. You have to just think of what is good to be together and what do you really want to have.
Okay. There's only 1 minute left, so let's wrap up. Could you make a short takeoff message, Tischer? So there's only one more question from Joel, but we don't have time. So
okay,
please
so
finish
I
up.
think my take-home message would be don't invent your own workflow management system unless it's absolutely necessary.
Very good. Tim, do you have some comment? Last comment? Final message?
No.
Okay, Tong?
Use Pixie, it's great.
Okay, Tong?
Yeah, just for software developers, think about large image data. They're important.
Okay, Tong? No. Sorry, Miguel.
I would say if you are a developer, just join the community, ask questions. If you are a user, ask questions. Most of the people out there in the forums are very happy to help.
Good. Thanks a lot. So make a clap. Thank you very much. So that was the show. And then, so our next seminar is in February, when is it? February 26th. And then this will be about Galaxy. So another workflow system. And then will be given by Beatrix, I think. Yeah. Okay. Thank you very much.
Thanks, everyone.